we will check into and learn more about how GitHub Actions can be used to meet these DevOps requirements. Dasher Technology is a software provider which offers a platform to facilitate the connection of data, applications, and devices across on-premise environment for businesses. Recently, their research and development team has been exploring the possibilities of transitioning their services to the cloud and leveraging container technologies. Initially, they aim to apply this to one of their Node.js-based projects with intentions to extend this approach to other projects developed in Java and Python at a later stage. So they have introduced a DevOps team for this initiative, which is led by Alice, who will be responsible for establishing the DevOps pipeline for the project right from its inception. And they also plan to adhere to the industry best practices. So their work will revolve under or around a multi-cloud infrastructure, utilizing Docker for containerization and Kubernetes for container orchestration. So Alice conducted a swift evaluation and learned that the current requirement penetrates to a Node.js project. So the previous team operated without a version control system, with developers, independently writing and manually integrating the code. The testing process was also sluggish and ineffective due to the manual execution. So collaboration among developers was often hampered as they worked on separate code branches with infrequent integrations and testings, and hence the software releases carried more significant risk. So deployment of software to various environments, including development, staging, and production, was primarily a manual procedure. So to tackle these challenges, Alice and her team have opted to implement a continuous integration or a CI/CD pipeline and have outlined the following key steps. So they want to adopt GitHub for version control and developer collaboration, implementation of unit testing and code coverage measures to expedite testing and minimizing bugs, utilization of Docker build and push processes for containerization, and the application is deployed to Kubernetes. And they also plan to incorporate automation like automated integration testing as a final step. The successful execution of these steps is expected to resolve the existing issues, and nevertheless, the team now faces an additional hurdle of selecting the most suitable CI/CD tool. So in the market, a wide array of CI/CD tools are available, which includes Jenkins, Travis CI, Bamboo, Spinnaker, Circle CI, and others. And after exploring several options, the team had made the decision to proceed with Jenkins, as it stands out as one of the most extensively used open source CI/CD tools. So to employ Jenkins, the team is required to undertake several tasks. The first thing is to do configuration, operations, and upkeep of a virtual machine with specific CPU memory and HDD capacity. And prior to Jenkins installation, prerequisites includes Java JDK installation, setting up firewall rules, and installing the Jenkins plugins. And finally, given that the project is centered around Node.js, so Node.js and NPM should also be installed. So to facilitate unit testing with various Node.js versions, the DevOps engineers must also install multiple Node.js and NPM versions packages, ensuring tests are run without any version conflicts. Docker installation is also essential for containerization. For Kubernetes deployments, the installation of kubectl, Helm, or other necessary binaries is mandatory. Apart from this, the team often employs external tools for integration testing and reporting. So these installations of the tools or their CLIs on the machine where Jenkins execute them should also be done. So it's also important to note that these tasks apply to a single Node.js project with high-level steps. So the pipeline complexity may grow with additional steps, proportionally increasing the manual configuration workload. Furthermore, the organization intends to implement similar methodologies for other Java and Python projects running on cloud platforms like AWS and Azure. So depending on the specific project, additional software requirements such as Java, Maven, Python, AWS CLI may be necessary. And if the pipeline demands enhanced security in line with DevSecOps practices, more tools like Trivy and KubeSec must be configured. So considering this DevOps team is recently established, many team members lack familiarity with a broad spectrum of tools and services. And since Alice has initiated a search for a tool that satisfies the following criteria. The first one is it should simplify the setup and initiation without the need to install and configure numerous services. And the second one is a focus on building pipelines without the burden of managing infrastructure or concerns regarding scalability. So following a thorough evaluation of multiple tools, Alice has chosen to check and implement GitHub Actions. So over the course of this training program, we will check into the creation of GitHub Action workflows for a straightforward yet a real-time Node.js application. Let's explore the importance of CI/CD. In a typical project, source code resides in a Git repository where it is both stored and versioned. So GitHub is a web-based platform which centers around Git, which serves as a centralized hub for hosting these repositories and extending Git's capabilities with additional features. Typically, all the code resides on the main or the master branch, which is frequently deployed to the production servers. When there is a need to introduce new features or simply modify existing code, developers create and collaborate on what's called as a feature branch. This branch essentially functions as a clone of the main code base, enabling a team of developers to work on a new feature until it's fully developed. Once the necessary changes are made, the code is committed to the feature branch and a pull request is initiated to merge the code back into the main branch. But before the merging takes place, a review process is initiated to carry out so that the changes require approval from the relevant team members or individuals. So following a successful merge into the main branch, the code is then deployed to production either manually or through an automated process. So this situation poses a significant risk to the application stability, as there is often no testing conducted on the newly merged code before it reaches the production environment. So in real-time scenarios, you often find multiple developers working on different feature branches, each focusing on a new enhancement. So performing multiple merges without the implementation of CI in a software development workflow can lead to several significant problems and challenges such as delayed testing, inefficient deployment, and quality assurance challenges. So talking about delayed testing, so without CI, testing typically occurs late in the development cycle, often after multiple merges have taken place. So this delay in testing can make it harder to identify and rectify issues early in the development process, which increases the risk of defects making their way into production. And talking about inefficient deployment, so again in the absence of CI, deploying code to various environments like development, staging, or production often relies on manual processes. So this can lead to inconsistencies in deployment and potential configuration errors. And the final one is about quality, right? So without automated testing as an integral part of the development process, ensuring software quality becomes more reliant on manual testing, making it prone to human errors and subject to resources constraints. So let's try to understand more about continuous integration. So let's imagine a scenario where developer 1 creates a feature branch and makes some modifications. And once the modifications are done, so they commit the code to the branch and a pull request is generated to merge these changes into the main branch. Again, before the merge, a team member reviews the code and an automated CI pipeline is triggered. The CI pipeline proceeds through several stages, which includes unit testing, dependency scanning, artifact building, and vulnerability code scans. All these assessments are performed on both the newly added code and the existing code, from the main branch. If any of this test fails, the developer is asked to make the necessary adjustments and commit the changes to the same pull request. This action triggers the CI pipeline once again, and if there are no failures this time, the pull request is approved and it is merged back, into the main branch. Upon merging into the main branch, the same CI pipeline, or possibly a different one with additional steps and tests, is automatically executed to verify the merged code. At this point, the testing the same code again after merging may seem redundant, but I'll try to clarify this by the end of the video. So while these deployments are taking place in a feature branch, let's assume there is a second developer who is progressing on feature branch B. So they commit their changes and create a pull request, and automated CI pipeline is initiated, testing the code committed in the branch. And once the CI pipeline is successfully completes, the pull request is approved and it is, merged back into the main branch. So following the successful merge, the main branch now contains the code changes from both feature branch A and B. And as mentioned earlier, any merges into the main branch is going to automatically trigger a CI pipeline. And in this instance, it once again runs all the tests, including unit testing, dependency scanning, artifact building, and vulnerability scans. This ensures that the code changes from both feature branch A and B work together. And the entire process, which enables multiple developers to work on the same application while ensuring that these new changes integrate smoothly without affecting the existing code or without introducing any new issues. It is called as continuous integration. So now that we understood the concept of continuous integration, let's also check the CD aspect, so which encompasses the continuous deployment, or it is all continuous delivery as well. So in the previous instances, after the code integration into the main branch and successfully completion of the CI pipeline, we manually deploy it to the production environments. So in many scenarios, even after rigorous CI and the testing procedures, it is advisable to deploy the modified applications to a non-production environment that closely resembles the live environments. So this allows for live testing before proceeding with the production deployments. So within the feature branch itself, following a successful CI pipeline, we can establish another continuous deployment pipeline. This pipeline is responsible for deploying the modified code to either a staging or a development environment. So following deployment, a series of tests are executed to ensure that the quality of the application is not regretted. So upon successfully completion of the CD, the pull request is then approved and merged back into the main branch. So within the main branch, the CI pipeline is triggered, assessing the newly merged changes. If successful, it automatically initiates the CD pipeline, resulting in the deployment of the application to the production environment. This automatic deployment process, following successful continuous integration, is referred to as a continuous deployment. In certain instances, a manual approval step before production deployment is a critical aspect of the development or the deployment process. This step serves to minimize risk, ensure quality, and adhere to the compliance requirement, and effectively coordinate changes. It also offers a safety net and allows for human judgment and oversight within an otherwise automated process. So in this scenario, often, after, the successful completion of the CI pipeline, the CD pipeline awaits a human approval before proceeding with the production deployment. The process of manual approval prior to production deployment is referred to as continuous delivery. Let's have a quick overview about GitHub Actions. So let's assume an organization has already decided to use GitHub as their code repository and is in search of an automation solution. So there are numerous tools available in the market to automate CI/CD pipelines. Nevertheless, given the organization's commitment to GitHub as the code repository, so let's explore how GitHub Actions offer the automation capabilities. So what is GitHub Actions? GitHub Actions is a powerful and flexible automation platform provided by GitHub. It allows developers to automate tasks directly from their repositories. You can quickly create workflows to implement a CI/CD pipeline that build, test on every pull request, and deploy merged pull request to the production right beside your codebase. Out of the box, these steps can be executed in different operating systems like Ubuntu, Windows, and macOS. And few advantages of GitHub Actions is that GitHub manages the infrastructure for you, which includes setting up the servers, scaling the resources, and managing the environments for your workflows. Your task is to write workflow configurations in YAML files, and GitHub Action handles the rest of the tasks. This includes executing the tasks within a virtual machine, caching necessary dependencies, and also providing reports on the outcomes. Finally, this automation also helps you streamline development, reduce manual errors, and increase the efficiency of your software development workflow. So, is GitHub Actions solely used for automating CI/CD pipelines for building, testing, and releasing code? And the answer is no. GitHub Actions goes beyond just CI/CD and lets you run workflows when other events happen in the repository. It can be used for automating all kinds of repository actions by listening to events such as push events, issues, pull request, GitHub registry packager events, or whenever an issue or a pull request gets updated. And these are just few of the trigger points. So we have a lot more other trigger points as well. So for instance, let's consider a scenario where a project contributor initiated a new pull request, and by utilizing GitHub Actions, you can automatically post informative comments, apply labels, assign contributors, and even add reviewers to assess and approve the proposed changes. These automation capabilities aren't limited solely to the pull request. You can employ similar actions for various other GitHub events as well. So now that we established the fundamentals of GitHub Actions, let's understand how and where these tasks are executed. The core component of GitHub Actions is a workflow. A workflow is an automated process capable of executing one or more tasks. These workflows are defined using YAML files and are located in the .github/workflows directory within your repositories. A repository can have multiple workflows, each of which runs in response to a specific event occurring in your repository. For instance, in this example, a simple event like pushing code to the repository triggers the workflow. And within each workflow, you define one or more jobs. A job consists of a series of individual steps which are executed on a runner. And a runner is nothing but a virtual machine which is responsible for executing your workflows upon triggering. So GitHub automatically provisions runners for each job based on the runs on configuration specified at the job level. In this example, there is a job named unit testing that runs 3 different machines. So it runs on Windows, Ubuntu, and macOS. So consequently, GitHub Actions will provision 3 virtual machines for this job, and these VMs are known as GitHub-hosted runners. So GitHub is going to host Linux and Windows runner on Microsoft Azure platform, while macOS runners are hosted in GitHub's own macOS cloud. And in this particular workflow example, all the runners are provisioned and operated in parallel. And after the runners are up and running, they start executing the steps, which are defined within the job. So in this example workflow, there are 3 steps, and the steps are executed in series. First, the runners will clone the repository locally on the virtual machine. Then they proceed to install Node.js and set up the necessary environment. And lastly, the Node.js tests are executed. So these same steps are executed on all the 3 runners concurrently. And consequently, if one runner completes all the step executions, it will be marked as successful, even if the other runners are still in progress of executing their remaining steps. The workflow as a whole is marked as successful only once all these 3 runners have completed the task successfully. So during or after the job execution, you can access the logs, outputs, and any artifacts for each step via the GitHub user interface. So this information is often received from the runners where the jobs gets executed. So within the GitHub repository, so we can simply navigate to the Actions tab to inspect the logs and the artifacts. So here, you will find that the unit testing job has been executed on 3 different machines, and you can review the logs of each of them individually. So this is going to allow for detailed debugging of the workflow progress and also to check the results. And if the job generates any artifacts, you can access and download them from this page as well. So GitHub Action provides a convenient interface for managing and retrieving any artifacts produced during this workflow's execution. And it's going to enhance the overall visibility and the usability of your automated processes. So now that we talked about runners, so let's understand the types of runners. So we have 2 types of runners, GitHub-hosted runners and the self-hosted runners. So let's try to explore the key differences, between them. So the GitHub-hosted runners, as mentioned in the name, are hosted and maintained by GitHub. So GitHub is going to provide a set of virtual machines with various configurations, including different operating systems and software environments. So you don't need to worry about managing the infrastructure of these runners. And whereas self-hosted runners are going to be, set up and run on your own infrastructure, such as your own servers, virtual machines, or even cloud. So you'll be having the full control over the environment, but you're also responsible for setting up and maintaining these runners. The second one is about the instances. So when you talk about the GitHub hosted runners, so they by default provide a new clean instance for each and every job execution. And in the self-hosted runner, we can run multiple jobs on the same machine. And the third point is, within the GitHub hosted runners, you cannot customize the runners beyond selecting the type of the runner. You can, such as Windows, Ubuntu, and macOS, but we cannot install additional softwares or make system level changes. So whereas in the self-hosted runner, you have the complete control over the self-hosted runner's environment. You can install any required software, configure the runner to your needs, and even use it to run workflows that require specific hardware or software configurations. And talking about the pricing perspective, so GitHub hosted runners are provided as part of your GitHub subscription. So they are usage limits. So if you, exceed the usage limits, you may incur additional charges. And whereas in the self-hosted runner, you bear the cost of, maintaining and operating your own infrastructure. So choosing between the GitHub hosted runners and the self-hosted runners depends on factors like your workflow requirements, security considerations, and infrastructure capabilities. So each of it has its own advantages, and the choice should always align with your specific needs. So in this video, we provided a brief overview of workflows, jobs, steps, and runners. So let's start by creating a GitHub account. We can navigate to github.com And you can use your existing accounts if you have one. So I'll be creating a new account here. So I'm just going to sign up for the free version. And let me provide some of these details. So you can give any details over here. I don't want to have any announcements. Let me verify. And that's it. I guess it should create the account. Okay, I need to enter another code. So let me just check my email. Okay, so let me just give in some more details. I'll just skip the personalization. And that's it. So it should initialize your dashboard. And this is a brand new GitHub account. I don't have any repositories. I don't have any settings. So let's go ahead and have a look at the settings. So I'll just go to the settings tab. And I'll just leave all the things as it is. I just want to check the billing and the plans. So I can click on billings and plans and usage. And as you can see here, I'm using the GitHub free plan. And this is the basic plan for all developers. And the points to be highlighted here are, so we are interested in these 2 points. So by default, in a free account, we get 2000 GitHub action minutes per month. And we also get 500 MB of package storage. So this storage can be used for both GitHub packages as well as GitHub Actions artifacts as well. Okay, so this should be more than enough for us to go through this course, do the hands-on and understand how GitHub Actions work. And if you scroll down, you should also see the usage minutes. So you can also download the report, like how many minutes you have used per month. And it also gives you some basic rates with respect to the Ubuntu, Windows, and the Mac OS virtual machines. And if you see here, the Ubuntu 2-core machine, it costs around $0.008 per minute, whereas the same vCores in a Windows virtual machine costs you 2 times about the Ubuntu machine. And if you talk about the Mac OS, it costs up to 10x compared to the Ubuntu 2-core machine. If you want to know more about billing and the prices, we can go and check out the documentation. If you scroll down, you also see the packages and how much space we have used in packages. And for actions and packages, I guess, yeah, this is the one which we will be interested in. So we get 500 MB included in the free plan. So any artifacts or any images which we are pushing to the GitHub packages, so it's going to display the limits and the storage options over here. And to conclude this, I'll just quickly go through the billing perspective. So this is within the GitHub documentation. I am within billing for GitHub Actions. And if you see here, this page talks about the all billing related stuff with respect to GitHub Actions. And we have various different plans. So we are currently in the GitHub free plan, which gives us 2000 minutes per month and 500 MB of storage. If you scroll down, it also talks about the minutes multiplier. So as we have seen in the earlier billing page, so the Windows cost 2 times the Linux virtual machines, and whereas the Mac OS cost you 10 times that of the Linux virtual machine. And if you want to look at the cost for different virtual machines with different CPUs, so you can have a look over here. So if you see here, the Linux machines, so these are the cost per minute for the Linux machines for different CPU cores. And this is for the Windows, which is exactly 2 times that of the Linux machines. And finally, we have the Mac OS runners or virtual machines, which cost approximately 10 times that of the Linux virtual machines.